Train Signal. You're watching a video about routing. In this video, we're going to start off by taking a look at routing tables. Make sure you understand how to read them, and we'll even take a look at how to access them. Then we'll take a look at the differences between static routing and dynamic routing. We'll go in and talk about routing protocols, which are used by routers to communicate with each other. And we'll break these routing protocols down into distance vector routing protocols and link state routing protocols. We'll talk a little bit about convergence, and then we'll wrap things up by looking at the differences between IGP and EGP. So, what is a routing table? Well, routing tables are used by network devices in order to determine where a packet should be sent in an attempt to get it routed to its final destination. Now, when we say network device, any network device, whether it be a computer, whether it be a router, or heck, it could even be a computer acting as a router, right? Because if you take a computer and you put two network cards in it and you have an operating system that supports routing, well, now you have a router that looks like a computer. But anyway, whether it be a computer, router, or any other network device, when it receives a packet, it takes a look at the IP address of that packet and says, well, all right, where do I send it? Where does it go? What do I do with this information? Now, if it's my own IP address, that's easy, right? I just keep it. But what if it's the IP address of another computer on the same network that I'm on? What do I do with it then? Or what if it's the IP address of a computer that's on a different network, or maybe we'll say the next network over? What do I do with it then? Or maybe it's the IP address of a network that's far, far away. What do I do with it? Well, the routing table is what is used to determine what you're supposed to do or what the network device will do with that packet. Now, the first thing I want you to take a look at here is I have a picture of a routing table on the screen here, and I want you to notice the different columns. Now, the first two columns, here we have the network destination and the net mask column. Well, just like we learned previously with IP addresses and subnet masks, and how they kind of go together, well, so do these. These go together to determine the list of potential destinations. In other words, when a device looks at the IP address on a packet, it needs to then figure out where in this table, okay, so where on the list that particular IP address falls. Now, let me clear that circle out of there so we can see things. There we go. What we want to do is go down the list, and so as a for instance, and I know this is kind of small and kind of hard to read, we'll look at a real routing table in just a moment. But right here, you'll notice it says 192.168.9.0 with a net mask of 255.255.255.0. What that means is any packet that has a destination IP address of 192.168.9. anything, well, that would fall into this particular entry. Now from there, the next column is the gateway column. Now the gateway column, and this is kind of confusing with the picture that I have here, but the gateway column is going to express what IP address I'm going to forward this particular packet onto. And you'll notice here, the top one has 192.168.10.200, and the rest of these say on link. And the reason they say on link is that means we're not going to send it off to any particular gateway or router, right? That's default gateway would stand for the default router. Well, gateway in this instance is a little different than when we talked about it previously where it was a protocol translator. Now gateway means router or possibly additional router or alternate router. On link means keep it right here. Send it directly to the destination IP address. And then the next column is interface. And this is expressing, well, what interface or which network card, we could say, that we are going to send the packet out on to get to that gateway. And then the last column is metric. And what metric has to do with is, metric is a number which it's a relational number which will determine which would be the best route if there's more than one. Okay, which would be the cheapest route, which would be the fastest route, Okay, and so you'll notice there's a number of different numbers here, some larger and some smaller. And the reason why is, again, if I come back over here to our first two columns, remember we had this one here that says 192.168.9.0, which means anything on the 192.168.9 network. Well, right below it, you'll see here we have 192.168.9.1 with all 255s, right? 255.255.255.255, which means now I have a second entry which would represent that specific IP address. Now, I will tell you that what we're looking at here is not the greatest example. So what I'm going to do is go ahead and click Start. And here I'm working with Windows XP, so I'm going to go ahead and click Run and type in CMD, which will open up the command prompt window. And then the command I'm going to type in is the route command. And if I just hit route and don't hit anything else and just hit enter, you'll notice that I get kind of a help of the route command. And there's a number of different selections that can be made with this particular command. And the one that I want is route space print. And this is going to not send anything to a printer, but it's going to print the routing table on the screen. So I'll go ahead and hit enter. And here you will see that I have a much shorter routing table on this particular computer. And actually, let me go ahead and let me expand this window, make it a little bigger so that we're not getting confused with what's in the background. So here you'll see that I have a much smaller routing table. And the reason why is because I'm just on a regular old Windows XP client. I only have just the one network card, and I'm connected to, well, one network. And you'll notice here that it talks about network destination and mask, just like we saw before. And I happen to be on the 192.168.10 network. That's the network that this particular computer is on. And so you'll notice that anything on the 192.168.10 network, well, the gateway is going to be in this right here, this .236. That's the actual IP address of my network card. So it's saying go to just myself, meaning I don't need a router, right? Routers are only needed to communicate outside of my network. If I'm communicating within my network, well, just send it directly to the destination via myself. I am the final gateway. But up here, you'll notice this 0.0.0.0, and that points to 192.168.10.200, and that's because that IP address represents, and it's listed down here in plain English, my default gateway. What that's saying is, if there is anything that falls into any network outside of what I have on my list right here, okay, this is kind of the catch-all, the default gateway. Send it to 192.168.10.200 and send it via the interface 192.168.10.236, meaning out the one network card that I have. Okay, so now if I had more than one network card, and if maybe I was acting as a router, then I would have additional entries on this routing table talking about other networks. So let me give you an example. I'm going to use that route command again, and I'm going to put route add. Okay, and this is for adding a new route. I'm going to hit space, and I'm going to put in the actual route. So let's say I want to know specifically what I would do if I were to receive a packet that was destined for the 192.168. Well, we'll say the 9 network, right? So 192.168.9.0 space, I'm going to type in the word mask, okay, and that's all you need to put in to enter in the net mask, space 255.255.255.0, right? I've now specified a network destination and a net mask, and all I need to specify next would be the gateway. So I'm going to put in 192.168.10, which would be another computer on my network, right? I can only send it to gateways that are on my network. So .10, and we'll say let's say 201. Let's say there's another router over at 201. Now I'm going to hit enter, and you'll see that, well, basically nothing happens. And so I'm going to type route print again to bring up a new routing table. me go ahead and scroll this down so we don't get things confused. And you'll notice that there's now an entry for the 192.168.9 network, but for this particular network specifically, we aren't going to send the packet to my default gateway. I'm going to send it to 10.201. That might be another router, and that might be the router that knows about the 9 network, right? The 192.168.9 subnet range. Now you'll notice down at the bottom here, they talk about persistent routes, and it says none. And the reason why is because this routing table, right here, this little routing table we have, well, this was established automatically just based upon the network interfaces that I have on this computer and the IP addresses that have been assigned to that interface, with the exception of this one entry that I just added. Well, if I were to reboot the computer right now, that one entry would go away. Okay, it's only good until the computer reboots. If I wanted that route to stay permanently, then what I would need to do is I would, and actually I'll tell you what, before I add the persistent route, let me show you this. Route delete. That's another route command I'll show you. All I got to do is just put in the network destination I want to delete, 192.168.9.0. If I hit enter, and then route print once again, scroll this up a little bit, you'll notice that that entry is now gone. If I want to add it persistently, well, then what I would do is I would go ahead and put in the route add command that I had before, exactly the way I did it the first time, with the only difference being that I'm going to put an extra space -p at the end. And when I do that and hit enter, now route print, you will see that we now have a persistent routing table entry that has been added. And what this means is even if I were to reboot the computer, that entry will still be there. It will be there persistently until I manually delete it. And then of course, how would I delete it? Route delete, and then just put in the destination, route print, and you'll see that the persistent route is now gone. Now, there are additional things you can do with the route command. I mean, you may have noticed that I didn't enter anything with regards to the metric. Okay, you could have also put in a specific metric with it. But for right now, the main thing I want you to focus on is the route print command for displaying the routing table, the route add command, knowing that you have to put a -p at the end, and it really doesn't even have to be at the end. You can put it at the beginning, but you need a -p to make it persistent, and then of course route delete to manually delete an entry. But other than that, this is exactly how any network device, in this case we're just talking about a client computer, but any network device knows what to do with a packet when it receives it. It takes a look at its routing table and figures out what to do next. Alright, so let's go ahead and put our command prompt window away and continue on here. Let's talk a little bit about static versus dynamic routing. Well, with static routing, all routers have to have their routing tables configured and updated manually. In other words, every entry in the routing table will be added manually, just like we were doing a moment ago. And it'll work just like what we saw a moment ago, meaning a typical router will have some entries in the table automatically based upon what network cards and IP addresses have been assigned. But outside of that, any additional routing table entries, like adding the .9 network, saying you need to go to a different router for that, that has to be done manually. As you can probably figure, that's pretty much a thing of the past. I mean, other than some isolated situations where we might have security issues, where we don't want to allow anything to be done dynamically, we might actually have a router that can only be updated statically. But you can imagine trying to go around in today's highly routed networks and manually update the tables of every router every time there's a change. It's just a nightmare. It would take forever, a lot of room for error, not a good thing. So that introduces us into dynamic routing. With dynamic routing, routers communicate to share their routing information with each other. And so what this means is administrators no longer have to go around to all the different routers and enter everything manually. Now, dynamic routing can be a little bit confusing to understand as far as how it works. So I want to do a little demonstration for you to help try to clear things up. Now, what I want you to do is I want you to picture that you are in the classroom with me right now. And this handsome little guy right here, that's me. I am standing in the classroom before you with my arms out at my sides. Alright, so I'm going to now demonstrate dynamic routing. Hi, I'm a router, and I'm attached to network A over here and network B over here. Now, I've been pre-configured with this information, but that's all I know right now. So, like I was saying to you before, a router will have some pre-configured information just by being turned on. In other words, if I'm a router, you turn me on, I'm connected to these two networks, I'm going to know about network A and network B, and I'll have a basic routing table right up here that says, all right, I know about A and B, and A's over on this side and B's over on this side. Okay, that's all I know right now. But then, hi there, I'm a router too. I not only know about network A, but on the other side of me, I'm connected to network C. Okay, and just like with the first router, this second router also is aware of networks A and C and has had that pre-configured. Great! I will keep that in mind if anyone over here is looking for network C. So what I've done is I've made an entry into my routing table that says if anybody is looking for network C, see, I don't know where network C is. But what I do know is that I can send it to this other router over here, okay, and it's going to go out through network A. Okay, so through network A, I can get to C, and it's going to be one hop. Now, what does that mean, one hop? A hop means the number of routers that the data is going to have to travel through before it can get to its final destination. Okay, or if you've ever heard the term next hop, that means the next hop is whatever the next hop in line, if you have multiple hops, the next router next to me. Alright, so continuing back to our demonstration. Hey, as long as we're sharing information, did you know that I'm also connected to network B? No, I didn't, but I'll make note of that for future reference. Okay, and then as you can see, this other router has gone ahead and has made an entry that says anybody looking for network B, well, it's going to be going to a router that's connected to network A, which I'm also connected to, and again, it'll be one hop. Oh, look, there's another router coming into the picture. Hello, I'm a router, and not only am I connected to network B, but the other side of me is connected to networks D and E. And so once again, you can see that this router has been pre-configured with a routing table that shows B, D, and E. Awesome! I'll keep that in mind if anyone over here is looking for those networks. So now, in the routing table of the first router, not only do we know about network C, which would be connected to another router off network A, but we now know about networks D and E, which are connected to a router off network B. Hey, and as long as we're sharing information, did you know I'm also connected to network A? Hey, that's good to know. And as you can see, routing tables are being updated. And here's something really cool. On the other side of network A is another router. No way. Yes way. And that router is also connected to network C. Cool. I'll update my information. Well, look what happened here. This router has now made an entry that says in order to get to network C, so if I get any packets that are destined for network C, I know that I need to send it to another router which is connected to network B, and I know that it's going to be 2 hops now before we get to the final destination. Okay, because it's going to have to go to this router first, that's 1 hop, and then this router next, 2nd hop, before it can go out to network C. Hey you, the router on network A. I just found out about another router on network B. Yeah, so what? Well, that router is also connected to networks D and E. I just thought you might want to know. Hey, that is good information. Thanks. And as you can see here, this router has now added D and E, each being 2 hops, each going out to another router connected to network A. And now all 3 routers are completely aware of all 5 networks, right? If we look at any one of these 3 routers' routing tables, we'll see the letters A, B, C, D, and E. Okay, in other words, there'll either be a network that router is specifically connected to, which would be these entries up here, or we'll know exactly where to send packets off to and what network it needs to be sent out onto to get there. And because this was told kind of like a story, we have to have a happily ever after. The end. Okay, enough fun with that. Now we need to move on and talk about how this actually happens. As far as, that's fine that we now know the basic logistics of routers talking to each other. But the way this is actually done is through the use of something called routing protocols. Now, routing protocols are divided into 2 different types. One type is what's called distance vector routing. Now, with distance vector routing, each router communicates all the networks that it knows about to the other routers to which it's directly attached. Matter of fact, that's a lot like the demonstration I just did, right? Each router is communicating the networks it knows about with any other router that it's connected to. Now, communication takes place on a regular basis when it comes to distance vector routing. Link state routing, what happens here is that each of the routers builds a map of the entire network. Okay, so it's not really just a literal, okay, I'm connected to this guy, I'm connected to that guy. It builds a map of the whole network. And LSAs, which stand for link state advertisements, are used to communicate information about the networks that they are connected to. But here's the thing. With link state routing, communication only takes place when a change has been made. Okay, so as opposed to regularly just going out there and saying, hey, here's what I got, hey, here's what I've got, hey, here's what I've got. Now, communication only takes place when there's been a change, when a router's been added, when a router's been removed, when a link goes down, when a link comes back up. So it may seem like link state routing is the way to go, but I'll tell you what. Distance vector routing is used way more often, and the reason why is because even though there's a lot more traffic and a lot more overhead as far as the network bandwidth goes, well, with link state routing, you have more overhead with the specific hardware that is used. Okay, you need to have more powerful hardware, and even beyond that, you need to have a higher level of sophistication with your administration and how it's all put together. And most people find that the network bandwidth is really not an issue with your distance vector routing. And as we'll see in just a moment here, there are distance vector routing protocols which now help to eliminate some of that traffic. So let's take a look at those distance vector protocols now. We have RIP, which stands for the Routing Information Protocol, and RIP actually comes in 2 flavors. There's RIP version 1 and RIP version 2. And then we also have BGP, which is the Border Gateway Protocol. Now, RIP is probably the most commonly used routing protocol on your internal smaller to medium-sized networks. Now, you'll notice here that in both versions 1 and 2, it supports a maximum of 15 hops. Okay, and the reason why they put that maximum in there is to help eliminate the potential circle that you could end up with. You could end up with A saying go to B, B saying go to C, C saying go to D, and D saying go to A, and A saying going to B, and B saying going to C, etc., etc. So that way, by only having 15 hops, you will prevent data from going round and round and round in an endless loop. Or more specifically than saying the data won't go around, you won't end up with routing tables that just continually grow in endless loops. Now, the first version of RIP originally had updates sent out every 30 seconds. Okay, and in the early days of routing protocols, this was not a big deal. But as networks grew, it really started to realize that this could be a problem. There could be a lot of data being sent out there. Now, another problem that we had with the first version of RIP is that it does not support authentication. Okay, so there's potential security issues there, whereas with RIP version 2, it does support authentication, which means you also have the ability now to have some level of control over who can update or what other routers can update the routing tables within a given router. Now, probably the biggest difference between RIP 1 and RIP 2 is that RIP version 1 uses broadcast communication. And what that means is that every 30 seconds a broadcast goes out. And all other routers who are programmed with RIP to go ahead and listen to this information will be bothered with this information. Whereas with RIP version 2, it uses multicast communication, which means only the other routers which are subscribing to the RIP communication will be bothered. And to be more specific, with broadcast communication, even other routers, or we'll say other nodes, other computers on the network that have nothing to do with this RIP communication, well, they're going to be bothered too. They won't necessarily have to acknowledge the information, but they're going to see it passing by. It's going to be tying up some additional network bandwidth there. Okay, so RIP version 2 is really the way to go. Now, what we also have here is the Border Gateway Protocol. And here's the thing I'll tell you. It's not used typically within internal networks. It's the core routing protocol of the internet, which means it is typically used by ISPs. In other words, the ISPs are using Border Gateway Protocol to be able to figure out how to communicate appropriately out with the internet. Now we have a couple of link state protocols. There is what's probably the most commonly known link state protocol, OSPF, which stands for Open Shortest Path First. It is used in your medium to large networks. Okay, when a network starts getting too large to realistically use RIP, that's when you go to your OSPF. But again, remember, with OSPF is going to come additional overhead. It bases its paths, or the paths that it'll send data, off what's called link states, okay, thus making it a link state protocol. In other words, it keeps a database of connections and whether they are in an up or down state so as to determine the best path. But it also could use cost metrics to give preference to certain paths. And that's one thing to kind of keep in mind, because cost metrics very often are used more with your distance vector protocols than with your link state protocols. And we'll talk about that in just a moment. The other one I have here is. And I think I just said is 3 times, right? It is, right? Well, is stands for intermediate system to intermediate system. And guess what? An intermediate system is another name for a router, which means basically this protocol is saying, hey, I'm a protocol that's designed for routers to talk to routers. Aha, that makes sense since we're talking about routing protocols. But anyway, I will tell you that is, you don't see it used too heavily out there. It was originally designed with the OSI model. It was designed by the International Standards Organization as part of the OSI model creation, as one of the original network layer routing protocols. Now, there can also be a hybrid of these two types of routing protocols. And some of the other protocols that we were already just talking about can be a bit of a hybrid. Some will refer to OSPF as possibly being a form of hybrid because it actually has some RIP functionality built into it as well. So there's a little bit of hybrid there. But the one hybrid routing protocol I want to talk to you about is the EIGRP, the Enhanced Interior Gateway Routing Protocol. Now, the Enhanced Interior Gateway Routing Protocol, as you might guess from the word enhanced, is really an update to IGRP, just the Interior Gateway Routing Protocol, which was a proprietary protocol that was designed by Cisco. Now, it uses something called the Diffusing Update Algorithm, or DUAL, to determine the best route to a destination. Now, okay, that's all fine and dandy. That's a whole bunch of extra letters for you to remember. But basically the way it works is that each router keeps a copy of its neighbor's routing tables so as to kind of work a little bit like a distance vector routing protocol, where it's kind of communicating with its neighbors and keeping track of their routing tables. And to be more specific, what it'll do is if it can't figure out, if a router using this protocol can't figure out how or where to send a packet, then what it'll do is it will query those neighbors in an attempt to discover an appropriate route. And what'll happen is that that query will then propagate onto further neighbors and further neighbors until some route is actually found. Okay, so you can see how this is kind of just that statement alone kind of makes it a little bit like distance vector and a little bit like link state. But to be a little bit more specific, the link state aspect of this protocol is that each router will periodically send out what's called a hello packet so as to keep track of the state of its neighbors, to know whether its neighbors are up or down, and that makes it like a link state protocol. So what is convergence? Well, when changes are made to a network, every router on the network will need to make the appropriate changes to their routing tables in order to accommodate these changes. Now, these changes could be the addition of a router, the deletion of a router, or it might just be some kind of a change in the metrics for a path. I mean, any kind of configuration change at all, well, it needs to be propagated to all the different routers in a network. So convergence is the process of all routers becoming aware of any change on a network. So for instance, in the little demonstration where I started off with I'm a router, well, really, as you saw, I'm a router I was 3 routers. And convergence was the process of all 3 routers talking to each other until they all knew about all 5 networks. That was convergence. And finally here we have IGP and EGP. Well, this is actually pretty simple. IGP stands for Interior Gateway Protocol, and EGP stands for Exterior Gateway Protocol. Now, these are not literal protocols. Like, there is no protocol actually called IGP or a protocol called EGP. IGP represents any routing protocol that is used to exchange information between routers within a LAN, or we could say interiorly. Is that a word? Okay, meaning in the interior. It's a routing protocol that's going to allow communication within a local network. Whereas, you'll never guess, but the Exterior Gateway Protocol is a routing protocol used to route information outside of the local network, typically out to the internet. And a very good example of an EGP would be BGP. Boy, these letters are really going to start getting confusing, aren't they? Because BGP is used by the ISPs to make connectivity out on the internet, thereby making it an Exterior Gateway Protocol. Alright, well, after watching this video, you should now be able to explain what a routing table is and know how to read one. You should also know the route command, or at least the basics: route print to display a routing table, route add to add an entry, and route delete to delete an entry. You should be able to explain the differences between static and dynamic routing. And obviously, static is kind of the old way of doing things. It's very manual. Dynamic's the way to go. You should be able to describe the differences between link state and distance vector routing protocols and know which ones are which. And you should be able to explain the differences between interior and exterior routing protocols. Alright, well, that's it for this video. I will see you in the next one.